All right, so we're recording now. We'll begin Wednesday, halfway through this week. And first thing, before we get started, where we left off yesterday, where we're talking about statically indeterminate structures, and that's what we're going to spend most of today doing, is solving a couple of problems that are statically indeterminate. But first, before we get into that, I was going to mention, make sure you're aware of the fact that I did finish grading your test yesterday, and I did two things in Canvas. One, I posted the solution to the test is now posted in Canvas. So if you're not aware of that yet, you can, log into Canvas and pull up the solution, compare it to what you did. Hopefully that will show you what you did wrong and allow you to fix anything. Going forward, you won't maybe make the same mistakes again. Also went in the grade book in Canvas, and it's been updated. So now that the grades in that grade book actually reflects your grade on the test. So if you haven't noticed that yet, you can check that out. A couple of pieces of information if you're interested or curious. I'll let you know the average on the test was 73.2, which is not bad, not great, but all things considered under the circumstances, not so bad. Can live with that. The high score was 100, so I think there was only one. There may have been, I think, also a 99 and several other 90s, but only one person was perfect, made 100. Anyway, just wanted to pass that along. Certainly look over the solution, and if you've got questions about something, don't understand why I did something I did, then you got to ask me, let me know, and we can talk about that later. All right, so now back to this was in your textbook, section 4.4, 4.5. Again, we're talking about statically indeterminate structures. These are structures that we cannot solve just using statics. And by that, I mean our three equilibrium equations. In order to solve these, it's going to take a combination of our equilibrium equations as well as what we know about deformation now. So we're basically just going to couple and put together two things that we already know. And let's start with this example. We are going to be asked to find the force and the two rods. I'll draw a picture in a minute. You'll see there are two rods that are holding up this beam. And also the vertical displacement of point A. So we want to find the force in the two rods and how far does point A move up or down. All right, so let me draw a picture now. We've got this horizontal beam, and it's supported with a pin support at the right end, point C. Out here at this end, we've got a rod that's attached. It's 1 meter long. And then here at point B, and I'm sure my picture's probably not going to be to scale. We got another rod here. It's 2 meters long. we're going to apply a vertical force. We're going to pull down between A and B with a force of 50 kilonewtons. And this is 0.5 meters, 0.5 meters, and then 1.5 meters. And let's see what else. So we're told that this horizontal member, the horizontal member ABC, it is rigid. So we're assuming it does not deform. It's going to stay straight. It's not going to bend. And we're given the cross-sectional area is 500 millimeters squared. And modulus of elasticity, 210 gigapascals. This applies to both of the rods. And so both of those rods are made out of the same material, and the cross-sectional area is the same. So they're the same size cross-section, both made out of the same material. And we're going to pull down here with this 50 kilonewton force, pull straight down. What's going to happen is this is going to rotate down about that pin support at C. It's going to stay straight since it's rigid. And we want to find, once we apply this 50 kilonewtons, what's the force in those two rods, rod at A and the rod at B, and how far does A obviously is going to move down. So that's what we're after. All right, so when we look at our free body diagram, as we draw the free body diagram of our beam here, we're going to have some force in that rod at A. I'll call it FA. There's going to be some force in this rod at B. We'll just call it FB. At our pin support, we got support reactions there as well. We have a horizontal support reaction, I'll call it CX, and we've got a vertical support reaction, we'll call CY. We've got our applied force of 50 kilonewtons. And again, the dimensions, this is 0.5 meters, 0.5 meters, and 1.5 meters. All right, so there's our free body diagram of our beam with all the forces acting on it. Now, if you just notice here real quickly, if you look, how many unknown forces do we have? We got 4. Right? So there's 4 unknowns. We got 4 unknown forces. There's no way we're going to find 4 forces with 3 equations. It just can't be done. So this is a statically indeterminate problem, and we're going to use a combination of our equilibrium equations and what we know about deformation. Well, first up, let's look at what we know from equilibrium. Our ultimate goal is to find these 2 forces, FA and FB. And so the equilibrium equation that comes to me first up would be, well, let's sum the moments about C. We eliminate those 2 unknowns, and we just have the 2 unknowns we're trying to find. So definitely going to want to make use of this equation. Sum the moments about C, and we'll go, I reckon, counterclockwise positive. So the 50 kilonewtons pulling down is causing a counterclockwise moment, a positive moment. 50 times 1.5 plus 0.5 is 2 meters. The 2 unknown forces, FA and FB, are causing a clockwise moment. So there would be negative moments. So minus FA times the distance to C is 2.5, I believe. And FB causing a negative moment times 1.5. So we've got this equation. We'll call this equation 1. So we get that from equilibrium. This is good. We got equation, it's got the two unknowns that we're after. Notice here, summing the forces in the x and y direction is not going to help us. Again, you don't have to do this, but I'll just write it to the side, just FYI. Summing the forces in the x direction, right? All that's going to tell us is what? Cx is 0. Which is okay, but not really needed. Right? If we sum the forces in the y direction, set that equal to 0. All that's going to tell me is FA plus FB plus CY minus 50 equals 0. Which, initially you might think maybe that would help us, but if you notice, we introduce another unknown. So we got our two unknowns, FA and FB, that we're trying to find, but we can't just pretend like CY doesn't exist. And so it shows up in the equation. So what we wind up with is we got equation 1 here, and then we'd have this equation, which leaves us with 2 equations and 3 unknowns. Can't solve it. I mentioned this yesterday, but I'll remind you, very important. What I see a lot of students do here, well, they're stuck because they need another equation, so they go and sum the moments about a different point. Maybe they come over here to point A and sum the moments. That does not give you a new equation. It will give you a multiple of this equation, I call it equation 1, or it'll be a multiple of this equation. You don't get a new equation by going summing the moments about a new point. You got 3 equations, that's it. These 3 equations, all we got to work with. So this is the one that's going to be useful to us. To get that extra equation is where we're going to make use of deformation. All right, so if I mentioned this a minute ago, what's going to happen, this horizontal bar, when we pull down on it, it's going to rotate about that pin at C. And so it's going to start out horizontal, and it's going to rotate, and it's going to stay straight because we're assuming it's rigid. Also, remember, it's not the first time we've talked about this, but the actual displacement is going to be really, really small. My picture here is greatly exaggerated just so we can see it. But this is going to rotate through a really, really, really small angle in reality. Right? I'm just showing it much bigger for illustration purposes. But as long as we're talking about really small deformation and small angles here, it is perfectly acceptable to assume that this point A is just going to move straight down. Right? We're neglecting the curvature here since we're talking about really small. And when we get to the end, one of the things we're asked to find is what is this distance that point A moves down? So when we calculate that, if it's really small, that validates our assumption. If we get delta A there is really big, and this angle turns out to be like 40, 50, 60 degrees, then our result's probably not so much accurate. But we're going to assume it's going to move straight down. Right? So point B is also going to move straight down. And I know the distance from A to B is 1 meter, and from B to C is 1.5 meters. And so this distance is going to be how far B moves down. I call delta B. Now, we know that delta A has got to be equal to the same distance that this rod at A stretches. Right, that's how far A is going to move down, is how far this rod here deforms. How far does it stretch? Likewise, B, it's going to move down the distance that this rod stretches. Right, so this delta A and delta B are the deformation in those two rods. Now, the relationship between those two, we could get several different ways. I think, if I remember right, did something similar the other day where I just used similar triangles. And so I'm going to go that way again. I know the deformation delta A there over 2.5 has got to be equal to this distance delta B over 1.5. And multiply both sides by 2.5. 2.5 over 1.5, it's like 1.666. I'm going to just round it to 1.67. All right. So just from the geometry, I know that's the relationship between those two distances, that point A and B move down. Now, back to what I mentioned a minute ago, I know delta A, that is PL over AE, right, for rod A. And delta B is how much the distance that rod B stretches, which I know is PL over AE, right, for rod B. Right, this is where we're going to get the other equation that we need to go with the first equation, and we'll be able to solve. So I know P, or the axial load, I called FA, so we'll call this FA. The length of rod A is 1 meter. The cross-sectional area, these are the same, so they're going to cancel out, but we'll go ahead and write them in anyway. 500 millimeters squared. If these didn't cancel out and you wanted to make sure units wise were compatible, we would need to convert that into meters squared. So that's times 10 to the negative 6. And E is 210. Giga is 10 to the 9 pascals. All right, so that's what PL over AE is for the rod at A. Do the same thing on the right side. We've got 1.67 times the force is called it FB. The length is 2 meters. And the area and the modulus of elasticity, again, is the same as it was for that rod. 500 times 10 to the negative 6. 210 times 10 to the 9th. But again, these are the same. We're going to cancel those. And if they're not the same, obviously we couldn't cancel them. But what we wind up with here is FA is equal to 2 times 1.666, or whatever you round it. I round it 3.34 times FB. That's my second equation. So I've got two equations now, both involving the two unknown forces, force A and force B. First one up here I got from equilibrium. This one I got from what we know about the deformation. And so now I'm actually able to solve for those two unknown forces. So take those two equations, and I'm going to skip the algebra here. So take equation 1 here, equation 2, two equations, two unknowns. I got force A was 33.9 kilonewtons. And FB 10.15 kilonewtons. Okay. And so that's how we're able to use a combination of statics and mechanics of materials to actually solve for these forces. We got one more part to this. We still got to find how far A moves down, but before we do that, Anybody have any questions about how we were able to find those two forces? All right. Well, now that we know what force A is, all we got to do is plug that in here and get what delta A is. Again, delta A, again, it's just PL over AE for rod A, and we know what everything is now. We know the force is 33.9. Those are kilonewtons, so I'm going to multiply by 10 to the third. Length is in meters, which is good. The area, 500 times 10 to the negative 6. That gives me meters squared. And then E is 210 times 10 to the ninth. Again, when you're doing SI units, if everything's in newtons and meters, you should come out good. And this is going to come out in meters. And we get something really small, 0.000323 meters. Now, a couple of comments here. One, right, this confirms or validates our assumption we made up here for the small angles and small deformation. That is 0.3 millimeters. Again, you would be hard pressed probably to even see that with the naked eye. That is really, really small. I don't know if you've looked at a ruler and see how far 1 millimeter is, but 0.3 millimeters, this thing barely moves. And so definitely our assumption here is valid. If you went back and actually included and took into account the curvature, you probably wind up with the exact same answer. But it requires a lot more work. That's why it's not done. Anyway, if this had come out to be 3 meters, I wouldn't put a whole lot of faith in that this answer here, because it's probably not valid. Other thing, it's very common if you're not careful with the units. You're dealing with really big and really small numbers here. And so I see all the time students will get an answer and they'll tell me like this is like 300 meters. Big alarm should go off in your head. There's no way this thing is going to move down 300 meters. The whole thing's only, 2.5 meters long? And more often than not, usually when you get a completely, unreasonable answer like that, it has to do with these units. Like, if you, instead of giga being 10 to the ninth, if you use 10 to the sixth, you just multiply this by 1,000. Or if you just do 210, you just went 9 decimal places. I've had it in the past. Somebody told me the displacement was so big it was larger than the distance between the Earth and the Sun. If you get some outlandish answer like that on the test, and you know it's wrong, write me a note and say, "Hey, I know this is way bigger than it's possible, but I just can't figure out where I messed up." I'll take that into account. If you don't tell me that, I'm assuming you think that answer is correct, which tells me you really don't understand, what you're doing here. And so you're going to lose more points than if you get a really wild, impossible answer and you tell me, "Hey, I know this can't be right. I just can't figure out what I did wrong." That's gonna save you a couple of points. So keep that in mind. All right, so this is very typical type of statically indeterminate problem where we've got more unknowns than we've got equilibrium equations, but we can get around it now. Any questions about this problem? All right, well then let's move on and look at a slightly different kind of problem. And before we actually work this problem, just kind of a little illustrative example here. I want to sort of talk about. This one is going to be more similar to, I think yesterday I talked about the other possibility is you don't necessarily have more than three unknowns. It's just the configuration of the problem makes it such that those three equations aren't sufficient. So look at this example. Say I've got this. Oh, let's see. We'll make the math easy. Something divisible by 3. So I got a 300-pound block. And I've got this, this block is attached with 3, so all 3 cables are, let's say 1 inch diameter steel. So I got a 300-pound block, and this thing's being held up with 3 cables. They're all identical, and the location also is symmetric. Right, got 1 cable at each end, 1 right in the middle. I would guess, and it's a little bit hard to do in this environment, but if anybody wants to volunteer an answer, you could probably tell me what's going to be the force in each one of these 3 cables. Just use intuition and common sense.
100.
100, right? You're going to have 100 pounds. All 3 cables out there. Each one is going to take equal share of the load, right? And again, that's just, again, intuition, symmetry, common sense, whatever you want to call it. That's correct. No work necessary. All right, well, what if I take this same 300-pound block, right in the middle, I've got 1 inch diameter steel cable, so that stays the same. But over here on the left corner, I'm going to replace that steel cable with a piece of kite string. And over here on this corner, I got a piece of sewing thread. Force still going to be the same in all 3 of those?
Yes.
The geometry is exactly the same, but I think most people would tell me there's no way that this kite string is going to have 100 pounds in it. It'd break. Same thing for the sewing thread. So what if in this configuration, what you would find is pretty much all the 300 pounds is going to be carried by that steel cable, and almost nothing. The force in those two is going to essentially be 0. Right? But again, just from observation, and our intuition and common sense would tell us this. So something's got to be going on other than just the geometry, right? Because the geometry is identical. Well, what makes the difference is what these cables are made of is what's different. The size is different. 1 inch diameter steel cable could take, I don't know, you can figure it out, probably, I don't know, it's probably 1,000,000 times what a piece of sewing thread could. It's a lot stronger. It's going to carry all the load. So this brings us to, say, look at this third scenario, where we got our same 300-pound block. We got our 3 cables still nice and symmetrically positioned. But let's say this is, again, a 1-inch diameter steel. Let's say this is a 3-inch diameter, maybe aluminum. And over here we got a 2-inch diameter bronze cable. Now, here's where our common sense and intuition is not good enough anymore. The force in these, we can't just look at and tell. The steel is stronger than aluminum and the bronze. So, that would tell you, it's probably going to carry more load. But in this case, it's also smaller than the other two as well. So something like this, we cannot just look at and say, hey, each one's going to carry 100 pounds. That's not going to be the case. It depends on the strength of the material and the size of that member. It's going to determine. So what we want to be able to do is, so how do we solve something like this? We can't just look at it and tell. Well, we're going to solve it same way we solved that first problem. We're going to use a combination of equilibrium and what we know about deformation. With those two things together, we can actually solve something like this. And we can tell it exactly how much force is going to be in each one of those members. All right? So that's the type of problem we're going to encounter next. Any questions just in general conceptually here before we actually solve a problem? All right, well then let's move to this problem. This one we got two different materials, and they're two different sizes. And let's see if I can draw this. What we've got is a steel reinforced concrete column. So if I can draw this. And again, I'm sure mine will not be to scale. So we've got this column. Eight feet tall. And again, this is concrete. And we've run a steel I-beam right down the middle of this, and I'm trying to draw sort of, it's supposed to be right in the middle, but again, this would be a steel I-beam. And dimensions, this is 16 inches by 9 inches. So it's a 16 by 9 rectangular column, concrete with the steel I-beam going down the middle. And we are going to apply a vertical compressive force of 60 kips. Now, in reality, that 60 kips, it's not going to be applied at one single point there. It would actually be spread out over the entire top of this column. That's just the resultant force of whatever that distributed load pushing down on top of this column that would be applied over the entire cross section. The resultant of that is 60 kips. And we put it right at the center, at the centroid, to avoid any bending. And so we want to find the stress in concrete and steel. And we're given some additional information. the cross-sectional area of that steel beam is given is 16 square inches. The modulus of elasticity of that steel is 29 times 10 to the third KSI. And E for the concrete is 4.2 times 10 to the third KSI. Again, those are given. Now, you would either be given those values in the problem statement like this, or if they told you the specific steel alloy, you could look up in that table and get the E. Same thing for the concrete. If they told you, what particular kind of concrete it was, you could look up in that table in the back of your book and get the modulus of elasticity. And typically, when you see modulus of elasticity, it essentially equates to the strength of that material. See, the modulus of elasticity for the steel is much larger than the concrete. The steel is a lot stronger than concrete. In fact, concrete really only good in compression. The strength and tension is essentially zero. But anyway, that's digressing. So we want to find, right, to get the stress in the concrete and the steel. Remember, sigma is P over A. So we need to know what the force in the steel is and what the force in the concrete is. If we know those, then we just do P over A to get stress, right? Well, the area of the steel is given, right? We know that. So maybe before we calculate the force, let's go ahead and get the area of the concrete. Now, pay attention and note that the area of the concrete is not 16 times 9. That would be the area of the concrete if part of it wasn't taken up by the steel beam, right? To get the area of the concrete, right, we're going to take the 16 times 9 and subtract the area of the steel I-beam. And this is, this was 16. So whatever 16 times 9 is, subtract 16, and I got 128 inches squared. So now we know the area of the steel and we know the area of the concrete. So now we need to focus on finding that force. So if you look at your free body diagram, you cut this member here, we've got 60 kips pushing down on this thing. And we've got the force in the steel and the force in the concrete. I'm going to denote just P, ST for steel and C for concrete. Now here's where so many students I see with similar problems, they say, well, like 60 kips, it's going to be 30 in the steel, 30 in the concrete. That's wrong, right? Go back to the sort of illustrative, our 300-pound block that we were talking about. Steel and the concrete, they have different strengths. They're different sizes. It's not going to be, 30 each. We can't get that from equilibrium. The only thing we can get from equilibrium, right, with some of the forces in the y equal to 0, if we take positive up, the force in the steel plus the force in the concrete minus 60 is 0. Right? The force in the steel and the concrete add up to 60, but we can't just look at that and tell that, hey, they're both going to be 30, right? Because they're different sizes, they're different material. Right? Everybody with me? Clear here where I got this equation and why each one's not 30. So this is an example. We only have 2 unknowns. Well, we got 3 equations, but the other 2 equilibrium equations don't help us. Summing the forces in X does nothing. All these forces are collinear. So you sum the moments about a point, it's not going to give you anything. Right? So We only get one useful equation from equilibrium. So that's why we have to rely also on what we know about deformation. Now in this case, we've got this big column and we're pushing down on that column. Well, in this case, whatever the deformation of that column is the same for the concrete and the steel. They're both going to get pushed down some amount. Right, so when we push this thing down some distance delta, it's the same for the steel as it is the concrete. Right? Everything's going to get compressed the same amount. So I know PL over AE, that's the deformation in the steel, it's got to equal PL over AE, deformation in the concrete. And so I call this P steel. The length is 8 feet. If we were actually computing this, we'd need to multiply that by 12 to get inches. The area, we had the area the steel was given was 16, and E was 29 times 10 to the third. As far as units go, notice this is KSI. Here, our force here is in kips. So we're okay if we leave this in KSI, our force is going to come out in kips. Just be careful unit-wise. You convert this to PSI, you need to convert that to pounds instead of kips. All right, and over here we got, I called the force in the concrete, PC. The length, again, is the same. Those are going to cancel anyway. The area we found was 128, and E for the concrete, 4.2 times 10 to the third. Again, KSI, as long as both of these are in KSI, this is in kips, our units are good. And then do some calculating with your calculator. I got 0.863 if you crunch all those numbers. And that's where we get our second equation from that we need, relates the force in the steel and the concrete. Got one up here from equilibrium. This one comes from what we know about deformation. Put those two together. And again, I'm going to skip going through the algebra. I got, somewhere I wrote this down, the force in the steel, I got 27.8 kips. Force in the concrete, 32.2 kips. And you see, they're not the same. They're not both 30. But that's what we needed in order to calculate our stress, being P over A. So at this point, to finish this is nothing new. We're just going to plug that force into P over A. So I'll pause here just a second. Any question on how we got those forces? And just point out, and I bring this up because I see students do this all the time. You see a problem like this on tests, and you say, well, force in the steel is 30 and force in the concrete is 30. You just lost a bunch of points because there's a bunch of work there that you didn't do. So that won't reflect good on your grade. So anyway, so to get the stress in the steel, we just take the force in the steel over the area of the steel. Notice this is compressive, right? This is the compression. So if we're going to use plus and minus for tension compression, we need to put our minus there. So it's going to be minus 27.8. I think it's 27.8. Again, that's in kips. If we leave it in kips, our answer will be in KSI, which is fine. If you don't like KSI, multiply by 1,000, get PSI. The area of the steel was 16, and where did it go? I got 1.74 KSI. Or again, if you don't like or use the plus or minus, put a C and tell me it's compression. Somehow, one or the other or both, you need to indicate it's compression. And then for the concrete, again, likewise, it's in compression. So I'm going to put the negative there, forcing the concrete over the area of the concrete. So 32.2, the area was 128 up there. And where to go? I got 0.25 KSI. And again, either plus or minus or T and C for tension compression. Right, so that's how we would go about doing this when we have, unlike the kite string and the sewing thread that I know is not going to take any load. Here, the concrete and the steel both going to take load. How much? Right, this is the process you got to go through to figure that out. Right? You can't just say, well, each one's going to take half. Right? Any question about this problem? Now, one thing while we're looking at this reinforced steel, reinforced concrete, I'll throw this question out there, and not necessarily expecting you to know this. Some of your civil engineers, you're going to see lots of steel reinforced concrete. Can anyone, tell me or have an idea, a thought of why do you put steel like this in concrete? Whether it's one steel beam or more commonly you see, rebar, just a bunch of steel rods in the concrete. Any thoughts or ideas? What's the purpose in putting steel in there as opposed to just being concrete?
Steel is really good in tension, and concrete's really good in compression.
Okay, and so we haven't got to this yet, but if you have obviously if you got a column like this where it is just being compressed, there's really not an advantage to putting the steel in there. But if that compressive force is not applied, the resultant doesn't act right straight through the centroid, or you have a member that's not just being compressed. And again, we haven't got to bending yet, but when you bend something, part of that member is in tension and part is in compression. And concrete, really good in compression, almost non-existent strength in tension. It just doesn't take tension. That's what the steel is in there for, is if you have a beam, something that's being bent, the steel is in there to take the tension load created by bending that the concrete can't take. You just take pure concrete and you bend it, it's going to break because the concrete just doesn't take tension well at all. And so that's why the steel reinforces either beams or bars or whatever is in the concrete for, is to take the tension if it's being bent. Anyway, that's just extra information, but first time we encountered this, so I thought I'd mention it. So just 1 minute left here. Tell you we're going to continue tomorrow, and the next section has to do with temperature change, and we'll study and talk about what happens when the temperature changes. That's the next topic on the agenda. If you want to look or read ahead about what we're going to do tomorrow, that's what we're going to do. Any other questions anybody has today? All right. Well, same invitation as always. I gotta do something here. Take me just a minute. I'm gonna. If there's no questions right now, I'll stop the recording, and then I gotta do something. It'll take me a minute or so. If you've got other questions you want to hang around and ask, after that, I'll be glad to do so. Otherwise, I'm going to stop recording.